Today we will learn about the quadrature amplitude modulation. Specifically, we will talk about the waveform Sm of t for quadrature amplitude modulation. And we will see the mathematical expression here. You will see the mathematical expression to show the waveform for QM signal. Then we will move forward to represent our Sm of t in terms of phi1 and phi2. You are familiar with this phi1 of t and phi2 of t. These are orthonormal basis functions, right? Phi1 of t and phi2 of t are orthonormal basis functions. When we say orthonormal basis functions, now it will have two properties. These are phi1 and phi2 are orthogonal, right? And their energies is unity. Normalized energies is unity. So if you find the expression for phi1 of t, you should be able to prove that its energy is unity 1. Similarly, if you see the expression of phi2 of t, you should be able to prove that its energy is unity. And the orthogonality property of these two should be verified. As we did it in earlier lectures, so I will not go to verify these orthogonality, which you can browse the previous videos and you can see how we verified. We will just use phi1 of t and phi2 of t, which are actually the two sinusoids, the cos of 2 pi f ct and the sine of 2 pi f ct. These are orthogonal. We will see its expression, mathematical expression, and we will represent our Sm of t in terms of phi1 of t and phi2 of t. Then we will move forward to derive the expression for the energy. We are always interested in the energy of the signal. So if we have this Sm of t, we would like to find out its energy, which we can represent by E sub m. We can represent it by E sub m. We are also interested in finding out the Euclidean distance, because when we represent our signal in orthonormal basis functions, it means that we can just represent our signal in using these functions, right? So it can be the signals can look like these signal points. So we would always be interested in finding out these Euclidean distance, which is the distance between the 2 points. Usually we are interested in the adjacent points, right? You can also find the distance between any 2 points using the same expression, which we will see while finding the Euclidean distance. But we will be interested in the minimum Euclidean distance. Why we are interested in the minimum Euclidean distance? The reason is the minimum Euclidean distance actually gives us information about the error rate, or the bit error rate, or the symbol error rate. The minimum Euclidean distance, based on we will see that the bit error rate expressions and the detection is mainly dependent on this minimum Euclidean distance. So if you have a higher minimum Euclidean distance, your symbol error rate reduces. So your symbol error rate reduces, it lowers. So minimum Euclidean distance, we will see that our symbol error rates in wide Gaussian noise, specifically when we deal with the wide Gaussian noise, this Euclidean distance play important role there. And simply, if I say it in simple words, it reduces your errors in data. If you transmit some bits or some data in from the transmitter at the receiving end, a signal constellation with greater minimum Euclidean distance would experience few errors as compared to the signal constellation which has higher minimum Euclidean distance. So this is important. This is important. We will see the expression for Euclidean distance, and finally the signal constellations will be shown for quadrature amplitude modulation. Specifically, we will see the circular constellation and the square constellation. So these two constellations we will observe. So let's start our lecture by we start by just defining our Sm of t. So we represent the quadrature amplitude modulation. Quadrature amplitude modulation, we represent it in this form as we write Sm of t, which is actually, we say it's the real part. It's the real part of a sub mi plus j a sub mq, then you have g of t and a complex exponential e raised to the power j2 pi fct, e raised to the power j2 pi fct. So this is the representation. This is the representation of Sm of t. I'll explain this complex form, because when we say the real of this part, this is actually, it means it's a complex number, and you can see it. We have a complex number here, right? This is a complex number, and we have a complex exponential here, right? So let's try to simplify it. Because our signals are real, so this exponential representation, we try to simplify it, and we want to see what our real signal would look like, because from here it's hard to see that what actually the signal waveform would look like. But of course, if you see this complex exponential, it's the sinusoid, right? And you have this complex number, so it has certain magnitude. G of t, we know that our G of t is real, and most of the time your G of t is either a gate pulse, a square pulse, right, or it is a raised cosine pulse. So whatever it is, our G of t is, we can say that it's a real signal. So we are familiar with our G of t from our previous knowledge, that this is a real signal. It is either a gate pulse or a raised cosine pulse, so it is real. Let's try to simplify this expression and try to find out what is the real part of this one, which is the representation of our quadrature amplitude modulated signal. So if you see the complex exponential, you are familiar. Let me write it specifically. The complex exponential, which is from the Euler identity. So you can always write the Euler identity, which is cos of theta plus j sine of theta. So this, we will use this Euler identity there to find out the real part of our Sm of t. And then you have another complex number, which is like this. It is in the form of a plus jb, right? A plus jb. It's a complex number. So we have a complex number here. Now about this complex number, you should know that if you are interested in finding out the magnitude of this complex number, it is from your elementary classes. You can say that this is a square plus b square whole under the root, right? And usually we are interested in the phase of this complex number. We can represent our complex number z in the polar form by using this magnitude and phase information. So if you are interested in the phase, it will be tangent inverse b over a. So this is the phase of your complex number. And if you want to draw your complex number in the axis, this z number, so you will have a here, right? This is a, and b on the another image, this part. B of course is real, but this jb is imaginary. So your number z is actually, this is your z, and you are interested in when you want to find out its magnitude, you are familiar with the Pythagoras theorem. So you have to square this and square this, and then take the under root, which we have done here, right? We have done it here. So this is how we try to find out the magnitude, and of course the theta. You are familiar with this theta as well. So you can say that, okay, this is my theta, which is given in this expression. So this is the theta. Now when you know all these parts, this one and the complex exponential, now we can find out the real part of this signal, and we will see how what actually this complex representation how we can simplify this complex representation. So let me simplify it. Now I would like to rewrite my Sm of t, which is the real part of ami plus plus j times amq g of t, and we had a complex exponential, right? Complex exponential, which is e raised to the power j 2 pi f c t. Now we do it step by step. We can say, okay, it's the real part of, let's multiply it, ami g of t and e raised to the power j 2 pi f c t, and then you have another part which is a j amq g of t and e raised to the power j 2 pi f c t, right? So this is after multiplication. Now if I use the same Euler identity, we will have the real part of ami g of t, and we have I'm just solving this one now, cos 2 pi f c t, and I can write a plus j am I g of t, and we have sine of 2 pi f c t, right? Now let's solve this part. This is plus j amq g of t, amq g of t, and you have cos 2 pi f c t, and then you have amq. Let me write it below here. I'll write it here. J. Now you have cos of 2 pi f c j Now I'm trying to solve. I'm trying to, let me bring it a little bit below. I'm trying to solve this part, right? This part. AMQ g of t cos of 2 pi f ct, and then we have plus j and sine of 2 pi f ct and multiplied by j. So j and j square, which will be minus. So instead of this plus, we will have a negative sign. So I'm just crossing it from here and I am writing it here minus or let me specifically write it and then we will multiply. Okay, let me write it and then we will multiply. We have j a m q, which is same as this part, g of t, and then we already have this cos, so we have j sine multiplied by j sine of 2 pi f ct, which is from the Euler identity, right? So now what we did this, we just apply this e raised to power j 2 pi f ct as the cos of 2 pi f ct plus j sine of 2 pi f ct. Now if you observe, let me close this bracket which I started here. I'll close it here. Now if we observe this one, if we take only the real part, so what is the real part? The real part is you can see the real part is this one is real, this is with j, so this one is imaginary. Now this part is also imaginary, it starts with j. If you see this part, this is j and we have a j here and a j here, which is j square minus 1, so this will become real with the negative sign. So actually our signal is now from this part and this last part. So our real signal looks like this. Our real signal is AMI g of t cos of 2 pi f ct minus is due to this j and this j square. So minus AMQ g of t and sine of 2 pi f ct. So this is your Sm of t. This is our Sm of t. This is our Sm of t, which is the real part of that complex exponential. Now if you see over here, if you observe, there is nothing complex. We have two real sinusoids. A cos wave and a sine wave. So we have two real sinusoids, and those real sinusoids are multiplied with this thing. AMI and AMQ are also real numbers. They are real numbers, magnitudes. And g of t is of course a pulse shaping waveform, a gate pulse. So basically your AMI and AMQ in this part, these are information bearing amplitudes. These are information bearing amplitudes. Information bearing amplitudes. So AMI and AMQ, it means if you have a data in the form of binary ones and zeros, so these AMI and AMQ would represent that data, and the symbol Sm of t, of course the symbol Sm of t carries the bits. So those bits, the AMI and AMQ depends on the bits. The rest is nothing but the carriers. These are the carriers. This is the pulse shaping waveform. So the only thing which is data dependent is this part and these real values AMI and AMQ, and we will see later on how to choose these AMI and AMQ based on the data bits 1 zeros, because the 1 zeros are required to be transmitted from source to destination. So this is the representation of our waveform Sm of t, which is a QM signal. The complex representation is actually made simple. This is your simple real waveform. Now if you observe it closely, the same, if we take our first expression, which I said that this is our first expression was a complex. It was in this form: AMI plus J AMQ. Then you have a pulse shaping waveform G of t, and then you have a complex exponential J2 pi FCT, right? So this was your representation of a QM signal, which we said that it is, because just the real, we are taking the real part, and the real part is this one, which represent two sinusoids, and they are multiplied with this pulse shaping waveform, and then the information bearing amplitudes, which are real values. These are real values. Now if you closely observe this part, we can have another representation. We can derive another representation, because this is just a complex number, and as I said earlier, this complex number can be represented in polar form. So when you want to represent it in polar form, which is in the form of this, if it is a complex number, now keep in mind, if it is a complex number, you can always draw it in this complex plane, right? Complex plane with the x and y with two x's. We will see that later on. We will see that this is actually phi 1 axis, phi 1 of t, and this is phi 2 of t. We will see it later on. So you can always draw it. This is phi 2. So we can always draw this in the complex plane, and we have AMI and AMQ. We have two coordinates, AMI and AMQ here. Suppose we have this in the complex plane, it looks like a point. So if it is a point, we can always write it in the polar form with the magnitude and the phase of this point, right? Magnitude and the phase of this point. So we can represent this part. We can represent this part in the polar form, and if we are interested in the polar form, then of course we would be interested in the magnitude of this one. And suppose I represent the magnitude by r sub m, so that magnitude would be equal to AMI square plus AMQ square, right? Which is just similar as we did earlier. And if we are interested in the theta m, the angle of this complex form, so that is tangent inverse of AMQ over AM S sub mi. So this is our theta. So actually this part, right? This is the theta. So we have this part over this part, the perpendicular over hypotenuse. So this is the tangent inverse. Now, if you have this r and theta, you can represent Sm of t. You can have another representation for Sm of t, and that can be actually it has certain significance. This another representation has significance. We can say, okay, we can rewrite it as r of m and e raised to the power j theta m. The real part of this rm e raised to j theta m, and the rest is same, j 2 pi f c t, right? So we just represent our complex form, our complex number am I plus j am q in this form, r of m e raised to power j theta m, which is the polar representation of that number. So so we just introduce this one. Now, what is the significance of this part? If you observe, we can rewrite it as r of m e raised to the power j 2 pi f ct plus theta. Right? We can rewrite it this way, and we can say that okay, we just say that if I want to find out the real part of this expression, it is nothing but r of m cos of 2 pi f ct plus theta m. So this is the real part of this expression. Now, what is the significance of this representation? Significance is here. We can observe our QAM modulated signal as an amplitude and phase modulated, as an amplitude modulation and phase modulation, a combination of amplitude and phase modulation. We can observe our QAM quadrature amplitude modulation as a combination of amplitude and phase modulation. See, you have each symbol Sm of t. Each symbol Sm of t has a unique Rm, the amplitude, and has a unique phase. So Sm of t has a unique amplitude and phase, right? So if you are right, you want Sn of t, which is another QM modulated symbol. It will have Rn and cos of 2 pi fct. It is same, just theta n will be different. So you have unique pair of Rm and theta m for each Sm. For each symbol you have a unique pair of the amplitude and phase, unique amplitude and phase pair. So this is it means that we can observe this representation shows us the property that our QM quadrature amplitude modulated signal, signal has a it is the combination of the amplitude modulation and the phase modulation. In amplitude modulation, we are only each symbol is distinguished by only amplitude. In phase modulation, each symbol is distinguished by only phases, right? But this is actually the amplitude and phase, both amplitude and phase modulation. So each pair, each Sm of t has a unique pair Rm and theta m. This would be unique for each Sm of t. Okay, we move forward to find out, to represent. Now we said that okay, with this Sm of t, we would be interested in representing our waveform in terms of phi1 and phi2. And you are familiar with phi1 and phi2. I'll just repeat it. You are familiar from your previous knowledge that we take phi1 of t as the waveform 2 over Eg cos of 2 pi fct, right? And phi2 of t, we take phi2 of t, which is minus under root 2 Eg sine 2 pi FCT, right? So these two are orthonormal basis functions. We are using these two orthonormal basis functions in our throughout in our modulation schemes. You multiple times we have proved their orthogonality, right? You can always prove that this the energy of this signal, each phi1 and phi2 energy is unity and they are orthogonal. So this negative sign, as I mentioned earlier, that you should not be confused with this negative sign, right? The negative sign which is here should not be confused with this negative sign. This is just to facilitate the expression, this negative sign. It has nothing to do with the orthogonality. It's still orthogonal, still the energy is unity. It is just to facilitate the expression so that you can write your signal as a summation. Instead of difference, you should be able to write Sm of t as a sum, not as a difference, as a sum of phi1 and phi2, scaled version of phi1 and phi2. We do not write it as a difference of scaled version of phi1 and phi2, right? So it's just to facilitate the expression. You want to write it as a summation expression. Sm of t would be, we will see it now, Sm of t can be expressed as a sum of these two, scaled version of phi1 and phi2, right? So let me move forward and I'll represent my Sm of t. I'll represent my Sm of t. Let me rewrite it first. Sm of t. I'll rewrite my Sm of t. If you go back to your first slide, we actually the next few slides we derived that Sm of t is AMI and G of t cos 2 pi FCT, and then we have minus AMQ G of t and sine of 2 pi FCT. We derived this expression. Now we want to write this one as a linear combination of phi1 and phi2. Now if you see phi1 already has this cos term. So if you observe it, this one, now if you observe phi1 already has this cos term. The cos term is already there. There are some additional scaling to under root 2 over Eg. So we need, if you want to express this in terms of phi1, how we can do it? We can write it. Now if I multiply phi1 of t with square root of Eg, if I multiply this one phi1 of t with square root of Eg over 2, so it will cancel out this part, this 2 of square root of 2 Eg. So I'll be left with the cos of 2 pi FCT, which I need actually. G of t is also there. Oh, I missed one thing. So let me rewrite it because I missed it here. In phi1 we also have this G of t. In phi1 we also have this G of t and G of t. In phi1 we also have this G of t, right? This gate pulse is there as well in phi1. So we can always prove that the energy of this is unity and they are orthogonal. Now if I want to represent, now let's see this representation. Let's see this representation. We are representing this part in terms of phi1. So if I multiply phi1 with under root Eg over 2, so this will be cancelled. I will be left with from from here it is just I'll be left with gt cos of 2 pi f ct, which is actually my it is present in Sm of t. So I just need to write AMI here. Now this part is same as this one. And in the next part I have a, if you see in Sm of t, I'll circle it. I'll circle this one. So let me circle this one. In the next part, if you observe the second part, this one, we already have this negative sign in phi 2 of t, right? We already have the negative sign in phi 2 of t. So phi 2 of t, I'll just write it now as I can write a plus here, because the negative plus phi 2 negative will already appear. Now I can just multiply my phi 2 with Eg over 2 and I'll get with this multiplication I'll get this thing. This is the same as this part. Now we are left with AMQ, so I'll write AMQ here. AMQ. So this is how you represent your Sm of t as a linear combination of phi 1 and phi 2. Now if you see, we are having summation here. This summation sign is we actually enter the phi 2 already have this negative sign, as I mentioned. Phi 2 already have this negative sign, so we have a plus sign here, and this is what we were trying, that we want to represent our Sm of t as a summation of phi 1 and phi 2. So this is the final expression. Now this representation has a significance. This representation has its own significance. If you observe this representation, now once you represent your Sm of t in terms of phi 1 and phi 2, you already know that your phi 1 and phi 2 are orthonormal basis functions, and they represent these axes, right? These axes. And now you can observe that your signal is just represented as 2 points. If you see, these are the, so we can write the vectorial form, the vector form of our signal, and we can write our signal in vector form Sm of t. In the vector form we use a different notation. I just use Sm, not Sm of t. So the vector form of my signal Sm is just these two coordinates, a mi and under root e g over 2 and a mq. Another point is amq eg over 2. So we have, in the vector form we have two coordinates. In the vector form we have two coordinates. So you can represent your Sm of t in vector form. This is the, I should write, this is the vector form of Sm of t. So this is the vector form of Sm of t, and you have two coordinates. You can represent these. You can represent this quadrature amplitude modulated signal as a single point now, and this single point has these coordinates. That is why we say that actually the image of Sm of t, over psi 1 axis is represented by this coordinate. This is the image of Sm of t over psi 1, because if you see your Sm of t is represented by this this vector, and its image which is this one, its image over psi 1. is just this thing, AMI. Similarly, its image over psi2, which is this one, this one. Its image over psi2 is represented by this coordinate. Another. So this vector representation is important, and we can always find these images using the dot product. Of Sm of t and psi1. So we already learned it earlier that if you want to find the image, if you want to find this, or you want to find this component, which we can say that, okay, our Sm has two components, which is Sm1 and Sm2. It has these two components, and you can always find these components, Sm1, which is the image of Sm of t over psi1. So we can always find it using the dot product of Sm of t over phi1 of t. Sorry, saying psi1, it's actually phi1 of t. So we can always find this dot product from minus infinity to plus infinity. So we can find Sm of t, which is the image of this signal over psi2. So if you want to write an expression for Sm of t, Sm2, which is the second image, it is Sm of t multiplied by phi2 of t, and you can always I would suggest that you go and prove this. You go and prove that your images are actually equal to this expression Sm1, which is your images are equal to this one and this one. You can just go and prove this, right? Just put these values and you will be able to derive it. So because we did it multiple times in the previous video, so I'll not do this calculation for you. So this is just the representation of the signal, quadrature amplitude modulated signal in terms of the orthonormal basis functions, and it has its own significance. Now, once you know these coordinates, we can easily find the energy of the signal now. If you know the coordinates, you are familiar that, okay, your Sm is Sm1 and Sm2, right? In the rectangular in the Euclidean space, you have 2 points Sm. For each signal point Sm has two coordinates, Sm1 and Sm2. So you can always find the energy of the signal. And using the constellation diagram, if we are interested in finding out the energy of the signal for a point which is in this which is here, it is just the from the Pythagoras theorem, you are actually having this is the square root of the energy, right? This is the square root of the energy. So the energy will be this distance is the square root of the energy. So the energy is the square. This is actually the square root of the energy. So if you are interested to find out this energy, you just need to square. You just need to square this one and this one, and we already have these Sm1 and Sm2. So it means our energy will be the square of Sm1 and Sm2. So if we are interested in finding out the energy of our signal, this will be equal to Sm1 square plus Sm2 square, right? So if you solve it, SM1 square, SM1 is AMI EG over 2, right? EG over under the root EG over 2, and that square plus AMQ under the root EG over 2 square. Now what do you have? You are left with the expression EG over 2, and you have inside AMI square plus AMQ square. So this is the energy of your signal. This is the energy of your signal, right? So the energy of your signal is the summation of these components. Now if you observe it, we have EG is usually a fixed value. The only data dependent amplitudes square to give us the energy of the signal. So we can always find this energy we can find the energy from here. You can also verify it from directly from your waveform. If you square it and integrate it, you will get the same expression. You will get the same expression for the energy. So this is the expression for energy of the QAM signal waveform. Now the next part is to find out the Euclidean distance. And Euclidean distance, keep in mind, when we say we are interested in Euclidean distance, you are representing your signals as points, right? Multiple points, many points in this Euclidean space. When we say Euclidean distance, we are interested in finding out the distance between the 2 points. So this distance, suppose you have a signal SM and you have a signal Sn, and you are interested in finding out the distance between these two. Why we are interested in finding out the distance? I mentioned earlier that this distance actually governs the bit error rate, or the error rate of the symbol error rate, or the bit error rate. So we are always interested in finding out the distance, and this distance again we keep in mind, if you are interested in finding out the distance, don't forget this Pythagoras theorem. It will be used again and again. So this distance, if you are interested in any, you can have this one, you can take this one. So let me clarify what actually the expression says. You have an expression for the distance. So if you have any 2 points in the space, suppose you are interested in this distance, right? This is the distance. Now if this is the distance, each point has 2 coordinates. You need this distance. You can find out from Pythagoras theorem, but for that you need this length and this length, right? You need these 2 lengths. If you know these 2 lengths, you can just say that, okay, my distance is equal to the square root of this length, the square of this plus the square of this, right? So the square of the perpendicular plus the square of the base. Now if, as I said, that you have 2 points SM and SN, suppose this is my SM, this is my SN. So my SM will have SM has 2 coordinates. So my SM will have 2 coordinates, which are SM1 and what notation we are using? SM1 and SM2, right? SM1, SM2. Similarly, your SN would have 2 coordinates, SN1 and SN2. I think we are using the same notation, SM1 and SM2, similarly SN1 and SN2. Now if you are interested to find out this length, what you would do, you would subtract SN1 from SM1 from SN1, or you can say, because we are taking the square, so you can also subtract SM1 from SN1. You can take any one and just subtract it. So this would be, this distance would be SM1 minus SN1 square, right, plus I can say SM2 minus SN2 square and whole under the root. So this would give us the expression for the Euclidean distance, right? This is the expression for the Euclidean distance. So if you plug these values in SM1, what is SM1? Now you can plug its value. It should be AM1, AM we can say AMI and AMQ. You can also say SM1 is SM1 is AMI. You can just comparing it with your previous notation, you can write that SM1 is AMI AMI under root EG over 2 minus ANI under root EG over 2, right? And we have to take this square. Now for this part we can say plus, let me write it below. I'll say, okay, my next part is A, or let me write here, my next part is AMQ, right? This is AMQ, because I'm just using that I and Q notation, AMQ under root EG over 2 minus ANQ under root EG over 2, right? So this whole under root is already there. This is whole under root. Now we have to take the square else. We have to take the square as well. Square. Now if you solve it, EG over 2, you can write it this way. From here, just try this one. You will have EG over 2 and then AMI minus AMI square. And from the second part, you will have again EG over 2. Now from this part, EG over 2, and you have AMQ minus ANQ whole square. So this is how you can just write it in a simplest form. EG over 2 can be taken common, and inside the bracket you have AMI minus ANI square plus AMQ minus ANQ square. So this is your Euclidean distance. We say DMN. This is the Euclidean distance. This is expression for the Euclidean distance. We just derive this expression. Now we are left with the representation. We are just left with the energies of the signals. So in the next part, and the signal constellation, actually the signal constellation and the energy of the energies of this signal. or we can let me continue here uh, to find out the energies. Now this is the Euclidean distance. If you observe your constellation, because we said that our signals are uh, a signal has two types of constellation, the circular as well as the square. And why we said that it has these constellation, the signal constellation. You can observe it as a phase and amplitude modulated signal. So if you have a phase and amplitude modulated signal, so you have a combination of, you can say, PAM and PSK. You have a combination of PSK. So your QM, quadrature amplitude modulation, is actually a combination of PM and PSK. So in pulse amplitude modulation, only the amplitude varies, right? Only the amplitude varies, and in pulse phase modulation, only the phase varies. So if we observe some constellation types, if we see, we can have just similar to the PSK. I can say that, okay, I have 4 points, these 4 points which are here on this circle. This represent PSK signal, and PSK signal with amplitude, one amplitude. Similarly, you can draw another circle outside this one, outside this circle, and you can plot some points there, because when we say we are QM, so we can plot some points here. You can say, okay, 1 point here, 1 point is here, 1 point is here. We have 4 points. So this is actually 8. If you say you have 4 PSK on the inner circle and 4 PSK, it's 8. We have PSK signal at the inner circle, this inner circle, and the outer circle also has a PSK signal, the same amplitude. But when we are using all these 8 points, so this is just a PSK constellation. This is just a PAM PSK combined PM PSK constellation, and it's a circular constellation for m equal to 8 QM. So this is MQM constellation. Basically it's MQM constellation with M8, and you can draw it. The circular constellation would look like this. Similarly, you can have a more complex constellation for M16. For example, if you have M16, 16 unique symbols, then the constellation, you have more circles. You can draw an inner circle here, the 4 points on this circle, then you have 4 points on another circle. You have 4 points. You can have 4 points on another circle, right? And you can have 4 points on the outer another circle. You can have another circle here, and you can draw these points as well. So when you are interested in just the 4 points we draw, these are the 4 points on the inner circle. Similarly, we have 4 points. We have 4 points on the outer circle, in the second circle. Then you can draw the 4 points on the third circle, right? The third circle, 4 points on the third circle. You can also have 4 points on the outer circle. So this keeps the Euclidean distance. Why we are drawing just 4 points? To keep the signal points far apart from one another, and that is important to get less symbol error rates, right? So you have for M16, this is the constellation looks like this. So this is the signal constellation for 16 QM. You can also have square constellation. You can also have the square constellation, and let's do it in another video, so that we do not increase the length of this video, right? We do not increase it too much. So I'll continue it in the next video.